Guys, before I start, go ahead and hit that subscribe button on BLACKPENREDPEN's YouTube channel. Okay, he's got really cool videos about a bunch of different math topics that everybody will be so delighted to see. So go ahead and hit that subscribe button, and well, let's see what we get. Hello everyone, welcome back to Mary Maths. And on this video, I'm going to do BLACKPENREDPEN's heat integral. Okay, that he proposed on his video on Cauchy's Strömlich, I think that's how you pronounce it, transformation. And well, let's try it out using his method from the previous video on the big integral. Okay, so for this integral, what we can do is, we can rewrite this as the integral from 0 to infinity of x squared divided by x squared, right? We divide by x squared on top and bottom, and then we have x to the fourth plus x squared plus 1, all of that divided by x squared times dx. And so we can simplify this to be the integral from 0 to infinity of 1 times dx divided by x squared, right? X to the power of 4 divided by x squared is x squared, plus 1 x squared over x squared plus 1 over x squared. Okay, so now what we could do here, is we can use BLACKPENREDPEN's method, which essentially is rewriting this as two different integrals, using the fact that the bottom can be completed, as a square, as a perfect square plus some number. So we can say that, 1, x plus 1 over x, all of this squared, will be a, right, a squared plus 2ab plus b squared. And if your a is x and your b is 1 over x, then a squared is going to be x squared, and then plus 2 times ab, which will be just 2, and then plus 1 over x squared. This will be a perfect square. So this is one thing we will want to get to in the denominator. But of course, in order to do that, we will have to make a transformation to the bottom, right? We will have to make a manipulation. So we will have to add 2, right? So we're going to have something like this. In the denominator, we're going to have something like this. So we're going to have x squared plus 2, right? We're adding 2 plus 1 over x squared, and then we're going to subtract 2 because we can change the value of that denominator, so we have to subtract 2 and plus 1, right? The one that's in the middle. Okay, and all of this can be simplified as the perfect square of x plus 1 over x squared minus 1. Okay, so that's equivalent to the denominator. However, we can also say that, because we know that x minus 1 over x, all of this squared, is also a perfect square, right? Which will be x squared, right? A squared plus 2ab plus b squared. Now, your 2ab is going to be negative 2, and then plus 1 over x squared. So it's very similar to the opposite, to the conjugate, but it's just different in the fact that it's got a negative 2. So to make the denominator, have a perfect square like this over here, and some number, we have to subtract 2 and add 2. So we're going to have something like this. We're going to have something like x squared minus 2 plus 1 over x squared, and then we're going to add back a 2, and we're just going to put the one that was in the middle. So we got this over here, and this is going to be x minus 1 over x, all of this squared, and then 2 plus 1 is 3, so plus 3. And notice that this is all equal to x plus 1 over x squared minus 1. We can use the fact that because they are equal, we can split it into two different integrals to our convenience. It's kind of like partial fraction decomposition, but it's not necessarily the same thing. So let's go ahead and split up the integral into two integrals. So we're going to have integral, okay, from 0 to infinity over here, and then we're going to have dx, right? We're going to have dx over here. Oh, I changed color all of a sudden. That's okay. So we have dx on top, and then on the bottom, okay, on the bottom we're going to have x minus 1 over x, right? So we're going to have x minus 1 over x, okay, and then squared plus 3. Okay, so this is just one integral. Originally on the top we have 1, right? So we can split it up into two integrals, so that the other integral is going to be the integral from 0 to infinity of dx divided by, okay, x plus 1 over x, right? All of this squared, and then minus 1. Okay, so these two integrals, okay, should be equivalent. But if we want to add them together so that it's equal to the original, we can just take a half of each, right? So we can just take 1/2 of each of them so that the top and bottom will be equal to each other, right? So we can multiply each of them by 1/2. So we can multiply by a half, so that 1/2 plus 1/2, right? We have to know that 1/2 plus 1/2 equals to 1. And that's essentially the same as this integral over here, because this has to add up, okay, over here. So 1/2 plus 1/2 equals 1, and we know that the denominators should be the same, so the integral didn't really change, right? But now, here comes the issue. If we want to use a u substitution, okay, for example, let's say that you want to use a substitution for this first integral of u equals to x minus 1 over x, okay, so that you can solve this easily, right? This looks like a tangent inverse problem, right? So if we find du, okay, du is therefore 1 and then plus 1 over x squared, the derivative of negative 1 over x. I have a hard time writing the 2 over here. Okay, there you go. Times dx. So what we know is that we only have 1 over here, right? So we would need an 1 over x squared. And if we add 1 over x squared, we will have to subtract 1 over x squared, right? And that's what we're going to do, but just wait for it. What if we do a substitution, w equals to, okay, for the second integral, equals to x plus 1 over x. It's all of this, okay? And then we have that dw equals to 1 minus 1 over x squared, the derivative, okay, of 1 over x, times dx. And look at that. What's the difference between this and this? Well, it's just the signs, right? They are conjugates. So essentially what we could do is we could add 1 over x squared and subtract 1 over x squared. Hence, we're not changing the value of the integral. So here's what we're going to do. We're going to add for this over here, because we're using the substitution of u, we're going to add 1 plus 1 over x squared dx. So it's just 1 plus 1 over x squared. Okay? And then we have times dx. And over here, we're going to add 1 minus 1 over x squared times dx. Okay, so that means that we can then use our substitution, okay, because here you see that we're not really changing the value of this. We're just adding 1/2 plus 1/2 of x squared, and we are subtracting, okay, negative 1 over x squared times 1/2, right? And 1/2 plus 1/2, well, is 1, so that all works out. Now we can go ahead and use our substitution. So let me call this integral number 1, and this is going to be integral number 2. So for integral number 1, okay, 1/2 times the integral of this, 1 plus 1 over x squared dx, divided by x minus 1 over x, all of that squared plus 3. We can use the u substitution. So therefore we have that integral number 1 is 1/2, okay, times the integral when x equals 0, okay, when x equals 0, over here, when x equals 0, you're going to get negative infinity, right? Because this will be 0 minus 1 over 0, which is negative 1 over 0, which is negative infinity. So it's going to be from negative infinity to infinity. When x equals infinity, okay, that's just going to be infinity. So it's going to be from negative infinity to infinity. Okay, so those are our new limits. And then we have du, right, du divided by u squared plus 3. And we know that this is a tangent inverse integral. So essentially this is 1/2 times tangent inverse, I forgot the 1 over a, right? 1/2 times 1 over a, and your a, well, is going to be the square root of this. So it's going to be the square root of 3. So 1 over square root of 3 times tangent inverse of your u, okay, u divided by a, which is root 3. Okay? And then the limits are going from negative infinity to positive infinity. So that's integral number 1. To evaluate integral number 1, well, we're going to have, okay, the limit. Usually, mathematically, to be mathematically correct, you know, we will take the limit. But I mean, it doesn't really matter. So let me just plug in infinity. Okay, so this is going to be tangent inverse of infinity, right? Okay, divided by 2 radical 3. And then we're going to do minus tangent inverse of negative infinity, okay, divided by 2 radical 3. Now, this over here is essentially, okay, tangent inverse of infinity is just pi over 4, right? So we have pi over 4 over 2 radical 3, which is pi over 8 radical 3. And then we have minus tangent inverse of negative infinity, because tangent inverse is an odd function. Therefore, tangent inverse, okay, tangent inverse of negative infinity is equal to negative tangent inverse of infinity. And we know that tangent inverse of infinity is pi over 2. I mean, it should be pi over 2. Yeah, so that means that this over here should be 2 times 2, which is 4. Okay, so that's pi over 2. So it will be negative pi over 2. Okay, therefore that's equal to pi over 4 radical 3 minus the negative of pi over 4 radical 3, which is equal to, okay, 2 times as much as pi over 4 radical 3, which is pi over 2 radical 3. Okay, so this is the value of the first integral. Now let's make sure that we calculate the second integral. So using our substitution for the second integral, okay, we have 1/2 integral from 0 to infinity, right, for x equals 0. And then let's see, when x equals 0, okay, what's going to be w? That's going to be positive infinity, right? It will be positive infinity. And when x equals infinity over here, then w will just be infinity, right? W would just be infinity. And what does that tell you? Well, what's the integral? Let's make our substitution. So dw is 1 minus x, 1 over x squared times dx. So that's dw. All of that divided by w, right? W is x plus 1 over x, all of that squared. So that's w squared minus 1. So now that we know the lower and upper limits, we know that the integral, okay, the integral from a to a of f of x dx is just equal to 0, right? So this integral is therefore equal to 0, which means that, okay, as a final answer, the integral, okay, from 0 to infinity of x squared divided by x to the power of 4 plus x squared plus 1 dx is just equal to, okay, the value of our first integral plus 0, right, the value of our second integral. So we have pi over 2 radical 3. And that's it for now. Thanks for watching.